Why don't we all stand up and stretch a bit, para lang magising tayo ng konti. It's a difficult time. Difficult time of the day. I know that a lot of you had experienced bad weather coming here, so I appreciate that you made an effort to come.
Yeah.
Sige, pwede na, no? Okay. There are participants in Zoom. No? You might not know this. There are a few participants in Zoom. I think last time there were 6 participants. Doon sa mga nasa Zoom, I'm not able to see you, I'm not able to see how many you are, for example, and I cannot see you also raising your hands. However, if you turn on your camera and you speak, lalabas yung picture ninyo dito sa screen, may screen dito, no, kung saan lalabas yung picture ninyo. No? So, if you want to ask a question dun sa mga naka-Zoom, what you have to do first, dapat una-una, mag-ayos kayo ng konti kasi bubuksan niyo yung camera ninyo, no? Baka makita ko pag binuksan yung camera niyo. And then you have to make an action to speak. You try to interrupt me by making an action to speak, and I will hear you and I can entertain your question. Okay? So, yan, may sample. Okay? Is this, are you a participant? Okay. Okay, so that's for the Zoom participants. Okay, so today I'm going to shift gears a little. Na-publish na yung first 2 set of slides dun sa Uble. And medyo naiba ng konti yung sequence nung pag-present ng material. No? I was expecting that the first material that would be presented would be what I lectured on last meeting. Pero iniba ng konti yung sequence, yun na yung hinuli. So I have to change my sequence a bit. So konting cambio lang ng konti. I'm going to present to you the material now that was already published in Uble. No? Tapos yung pinesend ko last time, I'm just going to adjust it a little. Kasi may mali dun sa mga gain values dun sa isang slide na pinakita ko sa inyo. No? The gains were too low. And then I'm going to publish that as soon as I adjust it. I just have been quite busy lately. And then dun sa mga gustong panoorin yung recording, that is recorded but I haven't published it yet. No? I'll publish it hopefully before the weekend. Okay, so what do I plan to cover today? Ito yung mga kukunin natin ngayon. No? We'll discuss process transconductance. Then we'll discuss channel length modulation. Okay. And then we'll go into MOS transistor biasing, although yung MOS transistor biasing, more or less, I think you already understand the basic concepts. But just the same, we'll go through that again. And then we'll discuss 2 possible biasing schemes. One is through resistance networks. So this is resistive bias. And then the other possible biasing scheme which we're going to take up is current mirrors, which is a very popular method of biasing your MOS transistor, especially in integrated circuits. And I'm going to explain why later on. Okay, so let's first discuss process transconductance. So ito yung mga equations natin for NMOS at saka PMOS. Equations for both linear and saturated mode. Okay. Iniba ko lang ng konti. Okay. You notice now that I put a subscript dun sa K. So dati-dati basta't sinabi ko lang 1/2 K VGS minus VTH squared. Ngayon, nakalagay na either Kn or K sub P. Depending on whether it is an NMOS transistor or a PMOS transistor. Okay, so a distinction now is being made between NMOS and PMOS. Yung case of N, ang tawag natin dyan, process transconductance for an NMOS. And yung case of P, that is the process transconductance for a PMOS. Otherwise, I haven't told you anything new yet. Okay, what is process transconductance? There's a formula for process transconductance. Okay. Case of N is mus of N, COX W over L. Case of P is mus of P, COX W over L. Where you already have been introduced to mu. Mu is mobility. That is mobility. No? That describes how mobile your charge carrier is in the particular medium in which it is in. So pag sinabi natin means of N, that's the mobility of electrons in the N channel. And means of P is the mobility of holes in the P channel. Okay? Now, one new term that I'm introducing here is oxide capacitance. Oxide capacitance, that is the capacitance of the gate area per unit area. Capacitance of gate area per unit area. Do you know the formula for parallel plate capacitance? Napag-aralan ba niyo yun sa physics, I guess? Anyone familiar? Yan. Ano yung formula for parallel plate capacitance? Anyone? Shout it out. Okay. C is equal to epsilon A over D. Does that look familiar to you? Epsilon is the permittivity of your dielectric, that is the material between your parallel plates. A is the area and D is the thickness. Okay. So the gate capacitance, let me call that C gate, that is the capacitance of the gate of your MOS transistor, is the permittivity of your dielectric. Your dielectric is silicon dioxide. So that is the permittivity of your silicon dioxide. Let me write that as E of silicon dioxide multiplied by A divided by what we call the oxide thickness. This is the thickness of your silicon dioxide. So this is your oxide thickness. And this is the permittivity of your silicon dioxide. Ang COX is just your gate capacitance divided by A. So this is just going to be the permittivity of your silicon dioxide divided by your oxide thickness. Now the permittivity of your silicon dioxide, that's more or less constant. Okay. Your oxide thickness, that depends on, of course, the process. Sa mga integrated circuits, when they build MOS transistors in integrated circuits, yung kapal ng oxide layer is in the nanometer. It's not unusual, for example, for the oxide thickness, for example, to be only 2 nanometers, 3 nanometers. Ganun kanipis yung oxide layer mo. So that allows you to have large values of capacitance, no? Because of your oxide thickness being small. No? So COX is actually farads. If you take a look at the units, this is going to be farads per square meter. And then W is the width of your channel. It's the width of your channel, and then L is the length of your channel. Okay. Now the width of the channel is more or less the width of the gate, and the length of the channel is more or less the length of the gate. How many of you have an idea how to solve the problem? Yeah. Okay, how many of you have no idea how to solve the problem? Please be honest. Okay, mahiya, no? If you have no idea how to solve the problem, then I would also adjust. Sige, take another, let's say, 2 minutes, no? 2 or 3 minutes. If this were an Uble quiz, you'd probably have about 10 minutes to do it, or something like that. I think we cannot take too much time on this. Please be honest with me now. How many of you think that you're close to an answer? Not so many. Not so many. Sige, let's do this. First of all, let me ask. What is the mode of operation of this transistor? Is it linear or is it saturation? Anyone? It's saturation. Why? Can you explain to your classmates why? Or are you guessing? I hope you're not guessing. No? Okay. Why is it saturation? Okay. Your gate is connected to your drain. Okay? Meaning to say, okay, meaning to say your source to drain voltage is going to be equal to your source to gate voltage. Right? Ito yung VSG. Ito yung VSD. No? Your gate is connected to your drain. Your gate is connected to your drain. That means your source to gate voltage is going to be equal to your source to drain voltage. Okay, what is the condition for saturation? The condition for your saturation is that your source to drain voltage should be greater than VDS SAT. But what is VDS SAT? VDS SAT is VGS minus VTH. Actually, when you're trying to, this I really suggest, no? When you're trying to determine whether your transistor is saturated or not, try to remember this curve, right? You try to remember this curve. You have a VDS SAT, and this is equal to VGS minus VTH, no? Where VGS is the applied gate to source voltage. This is ID, and this is VDS. Now, this is for NMOS, huh? NMOS. Ito PMOS to. Let's do it for NMOS. So when VDS is greater than this value, you're saturated. When VDS is less than this value, you're saturated. You're linear, no? Now your source to gate is equal to your source to drain. So ang magiging VSD SAT is VSG minus the absolute value of VTH. When this is equal, that means VSD is always greater than, no, VSG minus VTH. No? always. And therefore, you're in saturation. Therefore, you're somewhere here on the right. Okay, if you're in saturation, then price of D is just 1/2 case of P VSG minus VTH squared. Right? And so it's just substitution. Andiyan na lahat ng values, no? Alam ko yung case of P. Hindi, ito pala yung hinahanap ko, no? Ito yung hindi ko alam yung case of P, alam ko yung VSG. Okay, how do I know VSG? What is VSG? What is VSG in this case? Ano yan? Yeah, so, it's going to be 1.8 minus V sub O, which is 1. So that's 0.8. So VSG is equal to VDD minus V sub O. So this is 0.8. And then your VTH is just 0.5, no? So VTH is minus 0.5, no? So I sub D is 1/2 case of P. 0.8 minus 0.5, this is 0.3 squared. And that's given as 180 microamperes. Okay, so it can solve for case of P. Right? If you solve for case of P, anybody able to solve for case of P? Ano value? Ano yan? Case of P? Yeah, 4 milli, no? I heard it right. No? This is 4 milliamperes per volt squared. You might have made a mistake in some of your unknowns. So that's 4 milli per volt squared. So all you just have to do is now equate this to mu of P COX W over L. Right? Okay. Mu of P, that's mu of P WX, this one, that is given as 100 times 10 to the minus 6 microamperes per volt squared. Okay. W is what we're looking for, divided by L, which is 180 times 10 to the minus 9 meters. Anyway, when you solve for W, okay, unless I did something wrong with my calculator, you should come up with 7.2 microns. So that ends up being the width of your transistor. Yung pangalawang tanong, what should be the value of RD? That one is a no-brainer. Ano yung value ng RD? Siguro yun, dapat ano, no, instant makuha niyo yung value niyan. Okay, you're given V sub O, you're given I sub D. So RD is just V sub O over I sub D. 5.56 K. Okay. Any questions with respect to process transconductance? Okay. Any questions? Okay, the next thing that I am going to talk to you about is channel length modulation. Okay, channel length modulation. Okay, you remember the way we described saturation? Sabi natin, pag saturated yung transistor mo, hindi dapat magbago yung I sub D with VDS. In other words, I sub D stays constant for a particular value of VGS. No? This is for a particular value of VGS. Our I sub D will stay approximately constant. Unfortunately, that's not exactly the case. May konting pagbabago yung I sub D with VGS. Para palang BJT, parang BJT. Naalala niyo yung BJT? Okay, you remember the BJT? There's a slight increase in I sub C with VCE. And do you remember the reason? Yeah, it's the early effect. No? That's what we call that effect. We call it the early effect. But what is the reason? It's because of yung base width. When you increase your VCE, lumalaki yung depletion region between your collector base, the effective width of your base becomes smaller, and therefore there's less recombination in the base, mas madaming current na umaabot dun sa collector. Okay, so that is with the BJT. Okay, why does this happen? Bakit lumalaki ito? Okay, the reason for that is you remember pinch off, no? This is pinch off. Pinch off is when VGS, okay, pinch off is when the voltage between the drain and the source will decrease the electric field across your oxide layer, okay, so that the channel will disappear. You have to maintain a certain electric field across your oxide layer for the channel to be created. And that electric field corresponds to a voltage of VTH across your oxide layer. Kailangan yung voltage across the oxide layer is at least equal to VTH para ka magkaroon ng channel underneath your oxide layer. When that voltage becomes smaller than VTH, that is when you get pinched off. And that voltage becomes smaller than VTH when VTS minus VGS when VGS minus VDS is less than VTH. Yun na nga yung saturation. That's the point of saturation. So if you increase VDS beyond the saturation voltage, the point at which it will pinch off will move toward the left. Habang pinalalaki mo yung VDS beyond the saturation point, voltage, yun, no? Itong point na to, kung saan napipinch off, will move toward your left. Okay? And what you will have here is a depletion region. Magkakaroon dyan ng depletion region. I think I mentioned this in previous lectures. Just because it's a depletion region doesn't mean current cannot flow through it. It is depleted of charge carriers. But as soon as your charge carrier goes into that region, there's a very strong electric field here that will sweep your carriers across that region to the drain. And that happens also in the diode. No? The diode, there's a depletion region, pero dumadaan pa rin yung carriers natin. Okay. Kapag maliit yung change in the channel length, kasi ang mangyayari ngayon, magbabago ngayon yung length ng channel. Dati-dati ito yung length ng channel. It is the length of your gate. Okay? Dahil umatras dito, papunta dito yung pinch off, magbabago yung length ng channel. Magiging mas maikli yung channel natin. Kapag maliit itong delta L, you can neglect it. But if delta L is large, for example, if delta L is comparable to L, then you can no longer neglect what we call the change in channel length. And in integrated circuits, for example, because you're in integrated circuits, because you have millions of transistors inside your IC, ang nangyayari is your channel length actually is very small to start with. And therefore, this effect is more felt in the MOS transistors in your integrated circuit. Let me work out what happens. So originally, okay, my I sub D, sabihin natin it's an NMOS, no? Originally, my I sub D would be 1/2 mu of N COX W over L. So we already recognize this to be our process transconductance multiplied by VGS minus VTH squared. Okay, by the way, in the textbook, sometimes they say VTHN, no? VTHN. Pag nakita niyo yung VTHN, that's just to distinguish it from VTHP. Kasi pag minsan yung PMOS would have a different threshold value as your NMOS in the same circuit. So they would distinguish the two by VTHN and VTHP. If it's understood, you can just use VTH. Okay, so this is originally. Okay, if L is reduced by delta L, so yun yung nangyari rito, yung length nabawasan ng delta L, what will my formula look like? This will be I sub D is 1/2 mu sub n COX W is going to be L minus delta L VGS minus VTH squared. Does I sub D increase or decrease? Increase, right? Kasi nasa denominator yung lumiit yung denominator kaya nag-increase, no? So kaya ayan, tumataas, ano? Tumataas. Okay. For small values of delta L, okay, 1 over L minus delta L can be approximated to be 1 over L, 1 plus delta L over L. Okay. Now, how did I come up with this formula? I don't want to do the derivation here, but are you familiar with Taylor series? You've taken up Taylor series. You can derive this using Taylor series. No, you expand this function using Taylor series, and then you only have to get up to the second term. You can take out the succeeding terms. Ito ang lalabas. And intuitively, you can see that this is true. No? For example, let's say L. No? Let's take an example. Let's say L is equal to 100, delta L is equal to 1. Okay, ano yung left side? Left side is 1 over 99, di ba? The left side is 1 over 99. That is approximately equal to, what is the right side? The right side is 1.01 over 100. Okay. Di ba? Intuitively, kita nyo, malapit. Ano? 1 over 99 is very close to 1.01 over 100. Okay, so I can rewrite this now. Ito. Okay, this is now ID is equal to 1/2 use of n COX. Okay, W. Okay, 1 plus delta L over L. Tama, no? Oh, no, sorry. Divided by, hindi, tama. Tama. Teka, nawala yung 1 over L. No? Sandali. Okay, so W, 1 over L, 1 plus delta L over L, okay, VGS minus VTH squared. So this is now, okay, I'll just rearrange this and COX W over L VGS minus VTH squared 1 plus delta L over L. Okay. This is our original equation. Nadagdagan itong term na to. 1 plus delta L over L. Okay, how do I express that with respect to VDS? Because I want to get a relationship between ID and VDS. Delta L, okay, is proportional to VDS minus VTH. Kasi yung delta L natin would depend on how much VDS exceeds your threshold voltage. How much VDS exceeds your threshold voltage. When VDL starts to exceed your threshold voltage, doon nagkakaroon ng widening of the pinch-off area. When VDS is exactly equal to your threshold voltage, yung pinch-off area mo nandun sa pinakadulo ng channel. Tapos pag nag-exceed siya ng VTH, dun lumalapad yung pinch-off area. But we can neglect this, no? Just neglect this. Okay, so and we can say delta L over L, okay, is now equal to a factor lambda multiplied by VDS. Okay. And this is what you call your channel length modulation parameter. No? This is your channel length modulation parameter. Okay. This is dimensionless, delta L over L. And therefore, lambda must have dimension 1 over V. So lambda, this is a dimension yan is volts to the minus 1. Now 1 over lambda, we call this V sub A. Where V sub A is the parang siya yung early voltage ngayon ng MOS transistor. This is the early voltage of the MOSFET. Kasi pag kinuha niyo yung characteristic curves, so like what we did sa BJT, these are your MOS characteristic curves. And then you try to extend the saturation portion. Okay, lalabas, this is 1 over lambda. Okay, that is your 1 over lambda. This is ID versus VDS. Finally, our equation would be, I sub t is equal to 1/2. Okay, let me just write it as case of n. No, kasi ito case of n to. VGS minus VTH squared 1 plus lambda VDS. So this is an improved large signal model of the NMOS transistor in saturation. In saturation. So I'm sure madali na nyo ma-derive yung sa PMOS, no? So sa PMOS, it will be just I sub d 1/2 K sub p VSG minus VTH squared 1 plus lambda times VSD. So this is for your PMOS. Any questions? Any questions? Okay, let's move now to supposedly the central topic of this particular lecture, which is MOS transistor biasing. So again, what is MOS transistor biasing? This is selecting an appropriate operating point or cue point so that your transistor amplifier performs as you intended to perform. The Q point must be set properly for the transistor amplifier to perform as intended. So this is our example of your very simple common source amplifier. And we already studied last time. In fact, we were able to derive the voltage transfer curve. Ginawa na natin yan last time. So this is the shape of our voltage transfer curve, where we identified 3 points. A is your transition from cut-off to saturation. B is your transition from saturation to linear. And C is deep in linear operation. Okay. And we said that for a linear response, so that hindi distorted yung output natin, no? Para hindi distorted yung output natin, dapat yung bias point natin should be when it is in saturation. Our bias point should be somewhere here, somewhere in this area, when it is in saturation. Okay. And the choice of your bias point, may mga trade-offs yan. Sinabi ko na yan dati, ano? Okay, the trade-offs are your gain and your voltage swing. So if I choose a bias point here, as opposed to choosing a bias point here, you would have different characteristics. Like here, if I choose a bias point here, your tendency is for it to cut off more easily as your input signal decreases. Dito, it will not cut off as easily as your input signal decreases. On the other hand, here you see that your gain is also here. You see that your gain is higher. Here you see that your gain is smaller. So may mga trade-offs. Okay, the easiest way to bias your input, actually it's the input that you bias, no? But we say you're biasing the transistor. The easiest way is what we've done so far, which is to add a DC component to your input signal. So this is essentially what you're doing. Okay. Now, if you did it this way, how do you apply your input signal? Kapag ginawa nyo ganito yung pagbabias, then you have to apply your input signal capacitively to your gate. So if my input signal, if this is now my input signal, so this is going to be V small I would apply that capacitively to the gate. And that would have the same effect as putting this in series with this. This capacitor, we already mentioned, acts like a short circuit, or you have to select a value so that it's practically a short circuit at the frequency of your input signal. But this will act as an open circuit to DC. That's why we can handle the two sources separately. You can handle the DC component separate from the AC component. And then you can use the principle, so something like the principle of superposition, para kano sa superposition. Okay, so we're not concerned right now with this yet. We're just concerned with this. Okay. Now, if you had to provide a DC signal at the input of each MOS transistor in a circuit, think how many DC signals you would need. So you're going to come up with something like this. Let's say this is an integrated circuit. Ang dami mong magiging bias, ano? You might need V bias 1, V bias 2. Puro DC input na yung ano, no? Yung circuit mo, which is very impractical. So what is the solution? The solution is to create biasing circuits powered by the supply voltage of the entire circuit. So we have a supply voltage here. We derive V bias 1 using a biasing circuit, and we derive V bias 2 using another biasing circuit. So in which case, we only feed one DC input to your entire circuit. Now, what are the possible biasing circuits? So the easiest biasing circuit is the resistive divider biasing. In other words, how do I establish a voltage at the gate? How do I establish a voltage at the gate? The easiest way is through a resistor divider. So you remember the BJT, yung self-bias circuit? You also had a resistor divider's base. But the BJT resistor divider does not behave the same as the MOS resistor divider. Kasi dun sa BJT, kung naalala nyo sa BJT, right? If I may draw it here. Okay, meron tayong resistor divider dito. Okay, so this is, let's say, VCC, R1, R2. The difference in the BJT is, meron tayong current dito. There is an IB. No? IB is not equal to 0. And because IB is not equal to 0, you cannot say that VB is equal to VCC R2 over R1 plus R2. Hindi mo pwedeng sabihin yon. Pwede mo lang sabihin yon kung 0 itong current na to. Ngayon, luckily, in a MOS transistor, the DC value of your gate current is equal to 0. That is because your gate is a capacitor. Therefore, at steady state, the DC value of your gate current is 0. And therefore, we can use the voltage divider formula. So for a desired value of V sub G, all you have to do is select appropriate values of RG1 and RG2. Okay. Now, if this is actually connected to ground, okay, then V sub G, if this is connected to ground, then V sub G will just be VGS. Right? So, dito, okay, yung V sub G natin is actually the point, the VGS or Vin, yan na yung pinaka Vin, where you want your operating point to be. If I want my operating point to be, for example, at 1.2 volts, that means I want VGS to be 1.2 volts. That's what I will set V sub G to. So simple, no? You have a desired V sub G. If this is grounded, V sub G is also equal to VGS. Okay? And so you just choose the value of RG1 and RG2. Are there considerations for selecting RG1 and RG2? Yes, there are. Okay. Because I can select any value of RG1 and RG2. I don't want to select small values for RG1 and RG2. Why? Because it will consume a lot of power. Kapag maliit masyado yung RG1 at saka RG2, malaki yung current na daan sa kanya, and then the power dissipation will be large. If you're developing an integrated circuit, for example, that runs on a battery, and you want that phone you're developing to last you 5 days without charging or something like that, then you're trying to reduce the power consumption as much as possible. If you choose small values of RG1 and RG2, your power consumption is going to be big. And then but then, can I make it as big as possible? There are restrictions also for making RG1 and RG2 as big as possible. Because the larger your resistor, the bigger the area it occupies. So these are some trade-offs. Okay, and then you also have to take into consideration what is going to be seen by your signal source. Because here, we're only looking right now at the DC. But when your signal source is now connected, syempre may makikita din siyang resistance dyan. You also have to take that into consideration. So, you cannot just arbitrarily choose any RG1 and RG2. That's what I'm saying. No? You're going to get a better feel for this as we go through the course. Okay, now what are the problems associated with resistive divider biasing? So I already mentioned the area occupied by the resistor. Another problem is the tolerance value of resistor values. Specifically when these are discrete resistors. Ano ibig sabihin ng discrete resistors? For example, yung MOS transistor mo is a discrete MOS transistor. Discrete meaning pwede kang bumili ng isang MOS transistor sa tindahan. That's a discrete transistor as opposed to many MOS transistors fabricated in the same integrated circuit. So, discrete, ibig sabihin, nakakabili ka ng isa lang. And kung gagamitin mo to sa circuit mo, syempre ang gagamitin mo mga resistors din, yung mga binibili mo sa tindahan. No? Just like what you do in your lab. No? Have you experienced lab already? Not yet. Lab. Okay. Hopefully you experience lab soon. And when you buy resistors from the store, may mga tolerance values yan. Like you can buy the normal resistor that you buy from an electronic shop will probably have a tolerance value of 5%. Meaning to say whatever resistor value, they guarantee it's plus or minus 5%. Okay, if you buy a precision resistor, it can be plus or minus 1%, but it will have tolerances. And therefore the value of V sub G may actually fall within a range of values. Okay? And then there are considerations to like temperature. Sometimes temperature will affect your resistance values. Okay, remember that this is fixed by RG1 and RG2. Okay, so even if V sub G here is fixed, it's possible for I sub D to change. There are factors that can cause I sub D to change even if V sub G is fixed. There can be variations in I sub D due to process variations, for example, or change in temperature. Just to give you some examples, mobility varies with temperature. The higher the temperature, the lower your mobility. Your threshold voltage also decreases your temperature. Okay? And then your oxide thickness, when you go from device to device, especially for discrete devices, pwedeng nagbabago yung oxide thickness mo, so nagbabago din yung value ng COX. So there are certain things that can change I sub D, even if it is the same part number. No? Remember, oxide thickness is affects your K, no? Your process transconductance. That will affect also your I sub D. So a better biasing scheme allows IDQ, that is your quiescent current, to correct itself in case there are changes in temperature or process parameters. Yun yung hinahabol natin. We want, for example, no? Your temperature is rising. Your temperature is rising, so nagbabago yung IDQ. Ang gusto natin, yung biasing scheme natin will cause IDQ to adjust back to what its intended value is. Okay, and there's a very simple solution. And one simple solution is by simply just adding a source resistance. So ito, huwag nating ikabit diretso sa ground. No? Itong source terminal, let's not connect it directly to ground. Let's connect a source resistance here. Okay, intuitively, how does this work? Okay, let's just try to figure out how that works intuitively. Sabihin natin, tumaas yung value ng ID. Kapag tumaas yung value ng ID, tataas din yung value nitong IS. Kapag tumaas yung value ng IS, ano magiging effect sa voltage at your source? It will go up. The voltage at your source will go up. The voltage here is fixed by the resistor network. The voltage here goes up. So what happens to VGS? Ano nangyayari sa VGS? Bumababa. Tama? Kapag bumaba yung VGS, ano mangyayari sa ID? Bababa din siya. Right? So you see now how it works. Your ID starts to increase. Because your ID increases, the voltage at your source increases. Because the voltage at your source increases, the voltage VGS decreases, and because that decreases, it adjusts now ID to become lower. Itong resistor na to, we call this providing negative feedback. Because the voltage across your resistor is fed back to your input. This is your input of VGS, is fed back to your input, makes their input smaller. That's why you call it negative feedback. Okay. Now these are problems, or these are circuits na dapat sa'yo na you already are very familiar with in solving. No? Ever since EEE 123, you already solved circuits like this, and then you solved circuits like this again in module 2. So I'm not going to give any example anymore. No? If I give you a circuit like this, you should be able to compute for all of the voltages and currents in this particular circuit given the parameters of your transistor. So this is one way, itong RS. Okay, now, what effect will that have on the amplifier itself? You're going to see that later on. It fixes your quiescent point, it fixes stability of quiescent point, but later on you're going to see that will have an effect on the small signal behavior of your amplifier. As a matter of fact, it's going to reduce your gain. So again, trade-offs. There are trade-offs. Okay, here's a very simple scheme. Ito, simple lang. That provides a bias voltage at the gate and also provides a negative feedback mechanism. Okay. What is VGS here? Can someone tell me? What is VGS in terms of the quantities you see here, in terms of the variables you see here? Ano yung value ng VGS? Anyone? Anyone? Let me start. VDD minus IDRD. Meron pa ba? Wala na, no? That's it. Simple. No? VGS is VDD minus IDRD. In other words, we establish a voltage here equal to VDD minus IDRD. Okay, we establish a voltage here equal to VDD minus IDRD. So if we apply now our input signal, we will again apply it here, capacitively coupled. So in effect, this provides the bias. Yan yung nagpo-push nung signal natin to the right of your voltage transfer curve. Okay. Ask you a question. Anong silbi ng RG? Will RG have an effect on VGS? Yes or no? Who says no? No one says no. So RG has an effect on VGS. Actually, it doesn't have any effect on VGS because your drain current is your gate current is equal to 0, and therefore there's no voltage drop across RG, and that's exactly why VGS is equal to this value. So I could very well have actually used the short circuit. Okay, but again, there are reasons why you would put a resistor there, and that will be clearer later on, no? Because your input signal has to see a certain resistance value also. So that's going to be clearer later on. Okay, now how does the bias point adjust? Okay, how does VGS adjust? For example, if I's of D is increasing. It's very clear, no? If I's of D is increasing, okay, lalaki itong value na to, liliit itong value na to. So very simple feedback. You see that? So kapag lumaki to, okay, ito liliit syempre. And therefore automatically nag-a-adjust siya. So this is a very, very simple biasing scheme. Although it's a little bit harder to play around with the values so you get your correct bias point. No? And still, because this is going to affect your gain, parts of this is going to affect your gain, and also get the gain that you want. So it's not easy, no. Siguro, if your only concern was the bias point, then it's okay, no. You can adjust the value of this properly. But now, if you take into consideration the gain, then it's going to be like a balancing act. Any questions? So those are two different biasing, well, essentially three, no? Three different biasing schemes that we took up. Resistive biasing schemes. One is your simple resistor divider, but you saw that the resistor divider actually should include a source resistance, so that's the second. But then ito, quick and dirty biasing scheme where we just have a feedback resistor feeding back the drain voltage to your gate. Now, a very common way of biasing your MOS transistor is using what we call a current mirror. Current mirror. Okay. In your current mirror, this is your current mirror, ito. This is your current mirror circuit. Itong I of D, okay, which could very well be IDQ, no? It might be what you want to establish, no? It can be your quiescent drain current. Ito is established by this current source, IREF. And itong pagkakabit nitong Q1, we call this a diode connected MOSFET. Diode connected MOSFET. So what I'm saying is, diba yung symbol nito ng ng MOSFET? This, sorry, this is equivalent to this. Okay, that is equivalent to that. Why are those two equivalent? Like to think about it. Bakit equivalent? Okay, what is the operating mode of this? Pinag-usapan na natin ito kanina. What is the operating mode of this? This will always be saturated, right? Because your VDS will always be greater than VGS minus VTH. Why? Because VDS is equal to VGS. This is VGS. This is VDS. They're equal. The fact that this is shorted to this means this voltage is equal to this voltage, and therefore this condition will always be true. Right? So dun sa curve natin, we will always be on the right side of that line defining VDS sat. So this is always saturated. Okay, current is going to flow this way. If I try to make current flow the other way, So let me draw this again. If I try to make current flow the other way, what am I doing? By letting current flow this way, effectively, I am making this my drain, I'm making this my drain, and I'm making this my source. Because current always flows from drain to source. And this will be my gate. What will be my gate to source voltage? What will be VGS? It's right before you. Again, if I try to make current flow this way, effectively, kasi yung MOS transistor, remember that's symmetrical. Diba? Your gate can be your source can be your gate. It all depends on the voltages that are applied. So if I try to make my current flow this way, parang ginagawa kong drain yung source ko. Ginagawa kong source yung drain ko. Ito is still my gate. So what is VGS? Are you awake? What is VGS? It's right before you. What is this? Short circuit. What is the voltage across the short circuit? 0, right? So VGS is equal to 0. If VGS is equal to 0, will current flow? Will current flow? No, why? Because VGS has to be greater than your threshold voltage. So when I connect my MOS transistor this way, current can flow from up to down. But if I try to make current flow from down to up, my gate to source, my gate to the new source will be equal to 0. And because that is lower than your threshold voltage, current will not flow. That's why you call it a diode connected. That's why you call it a diode connected MOS. Because when you short your drain to your gate, current can only flow in one direction. You cannot make current flow in the other direction. Okay. Okay, so let's do this current mirror exercise. No? Wait. Sorry. Hindi ko pa pala na-discuss yung principle of the current mirror. Let me add another page. Okay, let's get expressions for ID and IREF. Get expressions for ID and IREF. So ID, that's for this particular transistor. This is for Q2. So let's say for Q2, ID is equal to 1/2 K. Sige, let's sabihin natin case of N, no, para masanay na tayong distinguishing between N and P. 1/2 case of N, okay, VGS minus VTH squared. Okay, let's assume lambda is equal to 0. In other words, let's use the simpler model of your MOS transistor. Assume lambda is equal to 0. That's for Q2. Okay, for Q1, okay, ID is IREF. You are forcing this current to flow through your MOS transistor. No? So yung ID natin will be IREF. Okay, which is 1/2 case of N. Teka, no? let's not assume you have the same Kn. No? So let's call this Kn2, and let's call this Kn1. No? Let's not assume that these two have the same process transconductance. Okay. So this is 1/2 Kn2 VGS minus VTH squared. Okay. Remember that the process transconductance depends on the dimensions of your transistor. So pwedeng magkaiba yung laki ng dalawang transistor. Now, if you take a look at VGS, VGS is the same for Q1 and Q2. Kasi yung gate nila nakakabit. No? So VGS for Q1 and VGS for Q2 are the same. And if this is fabricated using the same process, if that is fabricated using the same process, in fact, if those are two NMOS transistors on the same substrate, on the same integrated circuit, then most likely VTH will be the same for the two of them. So ito magiging pareho, ito pareho rin. So what is ID over IREF? ID over IREF, okay, is just now equal to Kn2 over Kn1. What is this? This is μs of n COX W1 over L1, and this is μs of n COX W2 over L2. So ito magka-cancel din yan. So I'm just, no, sorry, this is I2 and this is 1. W2, L2, W1, L1, sorry. So this is just W2 over L2 all over W1 over L1. Okay. In other words, if I want a particular current to flow here, right? Meron akong, let's say, alam ko na kung anong gusto kong IDQ. I already know what my IDQ is. That is my quiescent drain current. Okay. If I want a certain IDQ to flow, then I can adjust the sizing of these two transistors. Okay, so that given a certain reference, I can create the current that I want here, just by adjusting the sizing of my transistors. And a lot of times, it's actually the lengths are actually standard. It's actually the widths that we adjust. Madalas, no? Madalas yung lapad ang ina-adjust natin, yung haba is standard. Okay, so that's the principle of your current mirror. Now, why do you call it a current mirror? If the two transistors are exactly the same size, then ID rather is equal to IREF. And that's why you call it a mirror. Kung ano man yung current na padaanin natin dito, kung parehong-pareho yung laki ditong dalawa, same process, yun din yung current na dadaan dito. So the right side will always mirror the left side. That's why you call it a current mirror. Okay, we didn't take that up in BJTs, but actually there's also a version of current mirrors so BJTs, and it follows the same principle. If you tie the base emitter of two transistors together, assuming that the base emitter has exactly the same VI curve, then you get the same base current flowing in, and if the two transistors are identical, you should also get the same collector current flowing. Yun din yung current mirror sa BJT. Okay, so again, I have an exercise. Given two almost identical transistors, Q1 and Q2, you're given Kn, that's the same for both. You're given VTH, you're given L, but the widths are varying. Okay. Find IO if the bias resistor is 10K. No? Ito. Okay. I wanted you to solve this, but medyo wala na tayong oras, so I'll just present to you the solution. No? I'm not going to present to you the entire solution, but at least the outline. Then I leave it to you to complete the solution. Okay. Okay, so the first thing that you do is you have to compute for this VGS. So compute for VGS. Okay. VGS is equal to VDD minus IREF times R. Okay. VDD minus IREF times R should be the voltage at this point. VGS. Okay. But IREF, okay, is equal to 1/2 case of N, okay, VGS minus VTH squared. Right? Now here, okay, I have two unknowns here, IREF and VGS. I also have two unknowns here, IREF and VGS. So I can solve this simultaneously. Right? So everything else you know, no? You know VDD, VDD that's equal to 5 volts. You know R, which is equal to 10K. You know case of N, which is equal to 10 milliamperes per volt squared. And you know VTH, which is equal to 0.5 volts. No? And then, yeah, in effect, what we're computing for is itong IREF, no? What this IREF is. Okay, so you should be able to compute at this point for VGS. No? So that's quadratic. There's going to be a quadratic equation again. Huwag kayong maniniwala sa unang lumabas sa calculator nyo pag ginamit kayo yung solve. No? Better use the exponential powers of your calculator. Okay. Pag nakuha niyo yung VGS, then using either of these equations, ito mas madaling gamitin, then you can now solve for IREF. Okay. So now, IO over IREF is just going to be equal to W2 over L2 over W1 over L1. No? I know W2 and W1. Okay. Rather, I know W. Sorry, this is Q2. Again, mistake. No? Yeah, tama, no? So I know W1 and W2. Okay. And I know L. Itong L magka-cancel. Because L is the same for both. Okay, I already know IREF. I should be able to solve for I sub O. Okay, so try this on your own. Actually, this is part of the notes. And nandun yung sagot sa notes, no? I sub O should be equal to 729.2 microamperes. Okay, maybe one last topic. This is not part of the notes, but I just wanted to mention this. What if lambda is not equal to 0? What will happen if lambda is not equal to 0? So if lambda is not equal to 0, you have I1 is equal to 1/2 Kn1, okay, VGS minus VTH squared, 1 plus, assuming they have the same lambda, okay, 1 plus lambda VDS. Okay, then you have I2 is 1/2 Kn2 VGS minus VTH squared, 1 plus lambda. This is VDS1, no? VDS2. So now your I becomes dependent on your drain to source voltage. So if I get I1 over I2, okay, this is just going to be Kn1 over Kn2, 1 plus lambda VDS1 over 1 plus lambda VDS2. So this is going to be W1 over L1, W2 over L2, 1 plus lambda VDS1 over 1 plus lambda VDS2. So may adjustment lang tayo dito. Of course, magkukomplika nito, you now have to solve for VDS1 and VDS2 so that you can make the adjustment. That's it. That's what I wanted to discuss for today. So in summary, okay, we discussed process transconductance. We discussed channel length modulation, or we showed how ID is actually affected by VDS in saturation. So before we thought it was not, but it is. And we modified our saturation model so that you could take into account the effect of VDS on I sub T. Nagkaroon tayo ng 1 plus lambda multiplied by VDS, where the value of lambda is usually very small. And 1 over lambda can be thought of as something like the early voltage of your MOS transistor. Okay, then we took up biasing. So we took up very few resistive biasing schemes. Your resistive divider, which you actually should add a source resistance to, and then of course your drain to source resistor biasing, drain to gate resistor biasing. But sabi natin, a lot of instances, what we use to biasing is what is called a current mirror. Because sometimes it takes less space for you. In fact, not sometimes. No? Most of the time, it takes less space for you to fabricate a transistor than a resistor. It sounds odd, but yung kinakain na lugar ng transistor mas maliit sa kinakain na lugar ng resistor. So you would rather fabricate a transistor than a resistor. Nakakatipid kayo ng lugar. And then with a current mirror, you can very precisely control the bias current that you want to flow in your transistor circuit by just adjusting relative sizes of your transistors. Okay, we won't see each other next week. No? Use your break wisely. Use it to recharge. Kung may backlog kayo, gamitin nyo for your backlog. I promise that all the material will be published in UVLE by this weekend, so that you can already go through it next week, including hopefully the quizzes in the problem set. I'm splitting up. The module is actually going to be handled by 2 handlers. No? I'm going to be taking care of the second week material, and then see IZ is taking care of the first week material. Okay, so he published already all of the material. Yun nga, no? Nagkaroon na ng difference in sequence. That's why I have to go back to the sequence that we finally agreed upon. Okay, so I'm going to see you again Tuesday, week after next. Okay? Thank you.
Okay, sir.